Have you ever stood in front of a heater or a warm fire and felt a wave of heat wash over you? Even without seeing a bright light, you guessed it, that's infrared radiation. But this video isn't just about infrared itself. The truly weird part lies elsewhere. If heat is transferred by infrared, then why doesn't red light, which is right next to it on the spectrum, feel warm on your skin? After all, don't the photons of red light carry more energy than infrared photons? How is it that we feel absolutely no heat from a red traffic light or a red neon sign, yet an infrared source can warm us up from several feet away? If you've always assumed that red light should be warmer, stick with us. We're about to explore why that assumption is wrong, and how the invisible world of infrared possesses a power that visible light simply doesn't. In this video, we'll discover that the issue isn't just the energy of the photons. It's about where that energy is spent and how it interacts with our body that changes everything. We've also included the list of sources for you in the description section. Here are the fascinating chapters ahead. What is a photon? And do red light and infrared really differ? The wonderful infrared family, from near to far. The energy battle, red light photon versus infrared photon. The relationship between infrared, the sun, and the sensation of heat.
Many people think infrared is just red light that's turned invisible. This mistaken idea is one of the most interesting junctions in the physics of light and heat. Let's break it down step by step. Light is made up of tiny packets called photons. The energy of a photon changes depending on its wavelength, and our eyes perceive these different wavelengths as colors. Some colors have higher energy photons, and some have lower energy ones. But when photons hit a surface, they don't always cause heating. When a photon strikes an object, one of three things usually happens. 1. The photon excites the object's electrons. 2. The photon causes the object's molecules to vibrate. Or 3. The photon passes straight through the space between molecules. Red light, with a wavelength of about 620 to 700 nanometers, is part of the visible spectrum. Its photons have more energy than infrared, but most of this energy is spent exciting the electrons on the surface of your skin, a process that often results in the production of a new visible photon. Simply put, red light is mostly stopped in the most superficial layers of your skin, often less than half a millimeter deep. On top of that, your skin has a natural cooling system. Capillaries open up and quickly dissipate any heat. So even if a tiny bit of heat is generated on the surface, your body neutralizes it, and you feel nothing. But photons can do another crucial thing. They can make molecules vibrate. If a photon's wavelength and energy match the vibrational modes of the molecules in a liquid, for example, since liquid molecules have more freedom of movement, the photon's energy is converted into vibration and ultimately heat. If the wavelength is a bad match, the photon simply passes right through the molecules. In solids, molecules are packed so tightly that it takes much more energy to make them vibrate. That's why the wavelengths best suited to excite water molecules are useless against dense solids. A familiar example: in a microwave, the water in your food gets hot, but a dry ceramic cup or a rock barely warms up at all. Why? Because the microwave waves are vibrationally compatible with water molecules, but not with dense solids. By the way, Did you know that hot and cold are really just sensations and don't actually exist as actual physical entities in that way? If you'd like to know more about heat transfer, the link is in the description. We'd be honored if you checked that one out too.
Infrared radiation covers a massive range, from about 700 nanometers all the way up to several 100,000 nanometers. This range is divided into three main sections: near-infrared, mid-infrared, and far-infrared. If you're wondering about these names, it's simple. The infrared radiation with a wavelength closer to visible red light is called near-infrared, and those with longer wavelengths are named mid and far. The basis for this naming system is the visible red light. Near-infrared, NIR, is in the 700 to 1000 nanometer range. This section is very much like red light and is even used in some low-power lasers. Water molecules absorb very little near-infrared. Its wavelength isn't suitable for strongly stimulating their vibrations. Therefore, near mostly passes through tissue and has a high penetration depth, sometimes several centimeters. Consequently, it doesn't generate much heat. This is why red lamps or near-red LEDs don't create significant warmth. This characteristic makes near incredibly useful in medicine for imaging, low-level laser therapy, and deep tissue penetration. Mid-infrared, MIR, is in the range of 2.5 micrometers to 10 micrometers. Water acts like a sponge in the face of these wavelengths, absorbing almost all the energy. In the mid-infrared, the photon wavelengths perfectly match the vibrational modes of water molecules. Your skin fiercely absorbs these photons. Intense absorption means rapid conversion of energy into heat. This is why mid-infrared has a very low penetration depth. Almost all of its energy is absorbed right near the surface. The heat you feel from a furnace, a fire, and even the heat radiating from a human body mostly comes from this part of the spectrum. This is what creates our everyday sensation of warmth. Far infrared, FIR, is in the range of 10 micrometers to 1 millimeter. Water acts like a sponge in the face of these wavelengths, absorbing almost all the energy. But this intense absorption leads to low penetration. The heat remains in the superficial layers of the skin. A practical note: this is why FIR saunas, despite claims and advertisements, do not create deep heat. Their effect is superficial, not penetrating. To better visualize how different types of infrared interact with objects, imagine a glass of water that light is passing through. For short infrared, it encounters water that is like clear glass. The light passes through easily. For mid-infrared, it encounters water that is semi-transparent. Some light passes through, but a significant amount is absorbed. For long infrared, it encounters water that is completely opaque. Almost all the light is absorbed. This chart shows the absorption and penetration of infrared rays and its relationship with wavelength. As you can see in this chart, as the wavelength increases, the penetration into the skin layers decreases. Okay, the story isn't just what we've covered so far. There's another reason for the question we posed in the introduction. The world of physics is usually more complex than finding one short, simple answer to every question. Red light photons have more energy, but they are fewer in number, referring to common sources like lamps or the sun. In contrast, infrared photons have less energy, but they are much, much greater in number. And it's this sheer quantity that allows them to transfer a significant amount of heat overall. First, allow us to show you a couple of charts. We are, after all, a science channel, so it's only natural that we roll out some slick diagrams to show you that you're dealing with a serious science and documentary channel. Don't worry about their complex look. The concept behind them is very simple. Look at this first chart. In this chart, the horizontal axis is wavelength, and the vertical axis is relative photon energy, assuming the total energy of the beam is constant. This chart shows that as the light's wavelength increases, meaning the colors closer to red on the spectrum, the energy of the photons decreases. Now, let's show off a bit more. Take a look at this next chart. Here, the horizontal axis is wavelength, and the vertical axis is relative photon count, again, assuming the total energy of the beam is constant. This chart shows that as the wavelength increases, the number of photons increases. In simple terms, these two graphs are telling us one simple thing with a lot of attitude. Each red light photon has more energy than one infrared photon, but the number of photons reaching us from an infrared source is usually much greater than the number of red light photons. The result? You feel the infrared radiation as heat, but red light does not create that sensation. The sun emits the entire electromagnetic spectrum, but most of the heat sensation you feel on your skin comes from the infrared part. If you were to use a filter that only allowed visible light to pass and removed the infrared, the brightness would remain roughly the same, but the sensation of heat would be dramatically reduced. The wavelengths of red light and infrared are close, but the differences in penetration depth, type of absorption in the skin, and the quantity of photons are what cause red light to be seen brightly but not felt as warm. In contrast, infrared is invisible but felt intensely as heat. From now on, whenever you look at a red nightlight, an LED, or even a fiery sunset, perhaps you'll see it a little differently. Red isn't just a color. It's a boundary between the visible and the invisible world, a boundary between the magical displays of photons, energy, and quantum physics. Our world is full of amazing and sometimes incredible stories. If you found this video interesting, please like it and share it with your friends. Be sure to write your comments and questions in the comments section. We'd love to know which part of this story was most interesting or surprising to you. Stay curious until the next video.